Welcome to Lesson 1 from Learning Unit 3, Technologies for Functional and Smart Textiles. This lesson is part of the Mooc on Advanced Textiles Manufacturing Industry developed by the Hacktex project. This lesson presents a general overview of technologies for production of 2D and 3D smart textiles. The purpose of this lesson is to present the textile components specific to smart products, namely yarns and fabrics, their structure and the technology needed to produce such textile elements. The lesson is divided in 3 chapters. The first one will discuss functional and technological design of textiles used for smart applications for the design of smart textiles. The second chapter will present yarn structure and technologies. The third chapter will review methods of manufacturing 2D and 3D fabrics that can integrate smart yarns. Chapter 1. Functional and technological design of textiles used for smart applications. The design of smart textiles is a complex process that involves multidisciplinary knowledge for identifying optimum solutions to solve product problems. It makes this stage an intensive one and needs a deep understanding of the textiles throughout their entire value chain. Regardless of the type of the smart product, it involves non-smart and smart textiles. Functionalization and integration of smart functions can be done at each stage of the textile value chain. Product design must answer 2 major questions. What type of textile materials are best suited for the product, ensuring maximum efficiency, at lowest production costs possible? And what technological processes to use to obtain the smart textiles needed by the application? The answers are given by functional design, that defines structure and shape, and technological design that concerns manufacturing issues. Chapter 2. Technologies for 1D textile structures, yarns. Yarns can be produced from staple fibers, called spun yarns, and from filaments. Both types of yarns can be used to integrate smart fibers. Filaments can be made using smart polymers, or non-smart polymers can include smart polymers or other type of fillers. Composite yarns are produced combining spun yarns and/or filaments and are an efficient manner to impart electrical conductivity. Core spun yarns are obtained by twisting fibers around a core made of other fibers, most cases a filament. Wrap yarns are produced by wrapping a yarn around another yarn. Mechanical spinning technologies are employed to manufacture spun yarns, while filament yarns are produced using chemical spinning. Ring spinning is oldest and the most common spinning process. In open-end technologies, rotor spinning and friction spinning, the drafted fibers are collected by the tail end of a seed yarn. In air-jet spinning machines, a vortex created by 1 or 2 nozzles twists the fibers into yarns. Melt spinning is the most common technology to manufacture filament yarns, by extruding the melted polymers. In wet spinning, the polymers are dissolved in solution, while for dry spinning, they coagulate after solvent evaporation. Electrospinning is a technology with high potential for smart textiles. Chapter 3. Technologies for 2D and 3D textile structures. Basically, any type of textile material can be used to manufacture products with smart functions, most common being woven, knitted, non-woven and braided materials. However, woven and knitted fabrics are the most used types of smart materials, and as such, this chapter will discuss the structures best suited for smart applications and the weaving and knitting technologies to obtain them. 2D and 3D weaving. Weaving is a textile process in which 2 perpendicular sets of yarns, warp and weft, are interlaced to form a fabric. Woven fabrics are the most common textile materials and have different advantages for products with smart functions. Interlacing is obtained by passing the weft yarns over and under the warp yarns in a preset pattern. This process is carried out on weaving machines with different insertion mechanisms. The shuttle insertion mechanism was the first to be developed. The weft yarn is placed in the opening shed using a shuttle that carries the pern. For projectile weaving machines, the weft yarns are inserted using a metal device similar in shape to a projectile. The rapier insertion systems use a finger-like device to introduce the weft yarns. Another possibility to insert the weft yarns is to use fluid under pressure, air or water. From a structural point of view, woven fabrics can be grouped as simple and compound fabrics. Simple fabrics are made using only 2 systems of yarns. Compound fabrics are made with at least 3 systems of yarns and include double warp and double weft structures, triple warp and triple weft structures, 2-ply structures, made of 2 layers of woven fabrics, completely connected, compact fabrics, or partially connected. Multi-ply structures, with more than 2 layers, compact or partially connected. Warp interlock structures are obtained when several warp systems are interlaced with several systems of weft yarns. Special structures refer to pile, terry, leno and spacer. 2D woven structures, basic weaves. Plain weave and derivatives. It is the simplest type of weave, where the interlacing is obtained by passing each of the weft yarns over and under each of the warp yarns. The main derivatives are warp rib and weft rib, for which one direction maintains the 1/1 under interlacing, while the other interlaces with a different repeat, regular or irregular, and basket weave, where the warp and weft yarns are grouped and interlaced together. A twill weave is produced when the start of the interlacing pattern of the warp yarns is placed successively one weft yarn to the left, S-twill, or to the right, Z-twill. There are numerous variants of twill weave, mentioning zigzag twills and broken twills. Satin weaves are characterized by long floats of yarns visible on one side of the fabric. The interlacing of the two systems is not sequential, generating a uniform appearance. Satin weaves can be warp-faced or weft-faced. There are several classifications of fabrics with 3D geometry, the first being based on their three-dimensional shape. Solid 3D woven fabrics, with constant thickness or profiled. Hollow fabrics with partially connected layers, forming flat or uneven surfaces. Shell structures where the fabric can be placed in a 3D geometry. Nodal-shaped woven fabrics, obtained intersecting tubular structures, made using two-ply fabrics. The second classification criterion for 3D woven fabrics is the manufacturing method. Multi-layer, or multi-ply structures require the use of several warp and weft yarn systems, the warp yarns acting as binders from place to place, connecting the fabric layer to layer. Similar to 2 and 3-ply fabrics, when completely connected, will generate solid shapes, flat or profiled, and when partially connected, will generate hollow fabrics. The warp interlock structures are characterized by multiple systems of weft that are interlaced with multiple systems of warp. The fabric is connected through warp yarns called binder yarns, that traverse partially or completely the thickness of the fabric. If the binder yarns are placed at an angle in their path through the layers of yarns, the fabric has an angle interlock, while if the path is through the entire thickness of the fabric, then it is called orthogonal interlock. These 3D simulations present some examples of warp interlock fabrics. 2D and 3D knitting. Knitting is the textile process in which yarns are sequentially looped to form stitches horizontally, weft knitting, or vertically, warp knitting. The loops formed by bending the yarns around needles are interlaced with the previous ones. Stitches are the bricks of the knitted fabric, and they are placed horizontally in rows, or courses, and vertically in wales. There are two types of stitches, front stitches and back stitches. Knitting can be carried out on weft and warp knitting machines. Weft knitting uses flat and circular knitting machines, according to the shape of the needle beds. The most common flat knitting machines are V-bed machines. Circular knitting machines can have one bed, cylinder, or two beds, most cases cylinder and dial. Warp knitting machines can have one or two beds. Based on the geometry and position of the knitting elements, warp knitting machines can be divided into tricot machines, with 2 to 5 guide bars, high knitting speed, up to 3,000 rows per minute, used for less complex structures and for weft insertion. Rachel machines, with multiple patterning guide bars, lower knitting speed, up to 1,500 rows per minute, used for patterned fabrics and nets. The structure of knitted fabrics depends on the type of knitting, weft or warp knitting. 2D weft knitted fabrics can be obtained using the basic evolutions, simple or with patterns. The fabric structure controls the path of smart yarns in the fabric and their functionality. The basic weft knitting evolutions are plain or single jersey, produced on only one bed. Rib or double jersey evolutions produced on two beds, working alternately on front and back needles. Purl evolution produced successively on two beds as plain evolutions. Rows are transferred from one bed to the other, according to the evolution's repeat. Interlock evolutions result from the combination of two rib evolutions, formed alternately on one needle from each pair of needles, front and back. Another simple way of functionalization is by plating. Weft inlays and fleece patterns allow to integrate smart yarns without the stress caused by looping, especially suited for smart yarns. Inlaying of weft yarns is usually done using a rib or interlock evolution. Intarsia patterns are defined as fabrics with independent areas made of different yarns, connected by loops. Smart yarns can be integrated in preset areas. Warp knitted fabrics are produced on one or two beds. Apart from the basic lapping movements and their derivatives, patterns can be produced to change the fabric behavior and aspect. 2D warp knitted fabrics are obtained using three basic lapping movements and their two derivatives. Pillar is obtained when a yarn forms stitches on the same needle. Tricot lapping means a yarn will form stitches alternatively on two neighboring needles, while for atlas lapping, the yarn forms stitches in at least 3 wales. Derivatives for tricot and atlas are characterized by the fact that stitches are formed on non-neighboring needles. Warp knitted fabrics produced on tricot machines are made with at least 2 systems of yarns, most common being locknit, reverse locknit, satin. Partially threaded guide bars patterns, like pin net and fly net, have openings in the fabric, with preset dimensions and shape. Warp knitting technology is suited for weft and warp yarn insertion. Mesh structures are opened fabrics with preset geometry, that can be obtained using pillar and weft inlays, with the possibility of including other inlay yarns for patterns. 3D knitted fabrics. Both knitting technologies can be used to manufacture fabrics with 3-dimensional architecture, each with its own advantages and range of applications. 3-dimensional knitted shapes can be divided into multi-axial, spacers and shell structures. Multi-axial warp knitted fabrics are characterized by layers of yarns placed at preset angles that are connected by knitted stitches with pillar or tricot lapping. For spacer fabrics, the 3-dimensional architecture is obtained by knitting separately 2 independent outer layers connected by yarns or knitted layers. The latter connection is specific to flat weft knitting and it involves stopping knitting on the 2 outer fabrics and knit a layer that will connect both. Shell structures are manufactured only on weft flat knitting machines. They are 2D fabrics, with fashioning lines incorporated in the fabric plan. The technique, called flechage, allows to eliminate parts of the fabric plan by stopping progressively to knit on selected needles and then restarting to work on these needles. This way, there are areas in the fabric with considerably less stitches than the rest of the fabric. The areas with more stitches will be forced into a 3D geometry. This lesson discusses the concept of functional and technological design of textiles. Yarns, types and technologies used to produce spun yarns and filament yarns. Woven and knitted fabrics, structural characteristics for 2D and 3D fabrics and weaving and knitting technologies.